So in this graph, we're going to use our knowledge of parent functions and transformations in order to graph a child graph for any of the 4 functions that we have been studying this chapter. So just as a reminder, remember back in Algebra 1 and these previous few lessons, we've been studying the values of A, H, and K and how they all transform parent graphs. And these are our parent graphs with A, H, and K in the equation for linear, absolute value, and quadratic functions. So for this particular lesson, it might be useful to have 2 different colored writing utensils, such as colored pencils, because we're going to graph both parent graphs and child graphs onto the same coordinate plane. So here, what we need to start with is we need to start by looking at the function we've been given. And we can see the function we've been given is f of x is equal to 4 times the absolute value of x. So we need to identify which parent function we have, which in this case is the absolute value parent function. So it might be a good time to flip back to your notes on parent functions and look at the absolute value parent function, which is f of x equals the absolute value of x. So what we're going to do first is we're going to graph the parent function for our function. So if I look back at my notes, I'm just going to make a parent table here. And my table of values for my parent graph, if I pull my notes, I had x is -2, -1, 0, 1, 2. And then if I look back at my y values for the absolute value parent function, it went 2, 1, 0, 1, 2. So if I go over to my coordinate plane and I graph that, and I plot those points, I end up with that V-shaped graph that I saw before. Okay, so this black one I'm going to label as my parent function. That's my parent function, and I'm going to transform this in order to create my child graph. So the next part here says describe how the transformation will change the parent graph. So we have one transformation here. We have an A value that is equal to 4. And remember, the A values cause stretches and shrinks to take place. This particular graph, because it has a 4 out in front of the absolute value, is going to make it 4 times as tall. So this A value, if I just write a note in here, is going to vertically stretch the parent graph to be 4 times as tall. So we call that by a factor of 4. Now remember, a vertical stretch, vertical part of this coordinate plane is the y-axis. So what we're going to do is we're going to create a new table for our child graph. And because this child graph is being vertically stretched, we are just going to change its y values. And we're going to change its y values here to be 4 times as tall as the parent graph. So our x values stay the same. We have -2, -1, 0, 1, 2. And then from here, we're going to make every single y value 4 times taller because we are vertically stretching it up. So we take 2 times 4, which is 8, 1 times 4, which is 4, 0 times 4, which is still 0, 1 times 4, which is 4, and 2 times 4, which is 8. So we now have our new points that are going to stretch that graph to be 4 times as tall. So once we've applied all of our transformations, which in this case was just one transformation, we can go and we can plot the points on our graph. So here what we can do is we can go over and we can say, okay, we're at -2, 8, -1, 4, 0, 0, 1, 4, and 2, 8. So here if we graph, which if you use a ruler, your graph will look a little bit better than mine, you can see that this graph gets stretched up vertically and it is 4 times as tall. Now, our last step here is we need to identify our domain and our range. So I'm going to do that down below because I ran out of space a little bit. So the domain of my graph, if I'm looking at all of its x values, I notice it goes forever to the right and forever to the left. So my domain for my graph in blue only, I'm just looking at the child graph, is all real numbers. And then if I look at my range For my blue graph, which is my child graph, I notice that I need all of the y values that start at 0 and go up. So my range is y is greater than or equal to 0. So now we're going to go through that exact same process, but we've got a different paragraph with different transformations. So if we take a look at this particular function, what I notice is that this squared piece here makes my parent function the quadratic function, which is f of x is equal to x squared. So I'm going to go ahead and I'm going to graph that parent function. So I'm going to make a table down here. And I have my x and my y values. And if I look back at my parent function notes, I notice that in order to create this graph, I have x values of -2, -1, 0, 1, and 2. And then for the y values, I have 4, 1, 0, 1, 4. So I go over and I plot for my parent graph here, so I can see that u is starting. And then we go up there. So this black one here, remember, is my parent graph. So I've graphed my parent graph. I'm done with that first step. My second step then is to describe the transformations that will change the parent graph. Well, here I can see I have an h value of 3 and a k value of -4. So those two values are going to change my parent graph. I notice here that my a value, there doesn't appear to be one, and that's just because a is 1, and a is not going to stretch or shrink the graph for this particular problem. So we just need to focus on h and k. So h being a value of 3, remember h is our horizontal shift, so this one is going to shift the graph 3 units. And remember, it works the opposite of what we expect, so since it's positive, it's going to shift it to the left 3 units. And then k is our vertical change here, and it's going to move it down 4 units. So there are two ways to go about this. First, you can go directly to the parent graph and just start counting. Well, I'm going to move every point on this graph, left 3, down 4. The other option you have is you can use it in the table still, and you can look at the x and the y values, and you can actually say, okay, well, all of my x values are moving to the left, or in the negative direction, 3. So I can take all of these x values, and I can subtract 3. So we go, x is -2, subtract 3 more, x is now at -5. X was at -1, we're going to subtract 3 to move it to the left, so now it's at -4. This next one moves to -3, -2, and -1. So you can do that. If you like to use the tables, you can see that you're going to move it left, so you're going to subtract 3 from it to move it to the left. Then, for the y values, we know we're going to move it down 4. And as a result, we need to take each of these points and move them down 4 along that y-axis. So here 4 minus 4 is 0, 1 minus 4 is -3, 0 minus 4 is -4, so on and so forth. So you can use the tables if you want, or you can go right to the parent graph and you can say, well, this graph is going to move left 3, so I'm going to take this point and move left 1, 2, 3, down 1, 2, 3, 4, which if you look is exactly the point I expected here. It's the point x is -5, y is 0. And then I plot the next point, so I can go left 3, down 4, or I can go directly to x is -4, y is -3. It's going to get me to the same place, left 3, down 4, or just utilizing the table. Then my next point is x is -3, y is -4, x is -2, y is -3, and -1, 0. So you can see that we've taken this parent graph and we have shifted it to the left 3 and down 4, just as those transformations told us they would. Now, our last step here is to identify the domain and the range of this particular graph. So if I look at my x values, I'm using every point to the left and to the right. So my domain is all real numbers. And then for my range, this one is actually a little bit trickier. Our range, our lowest point is at y is -4 and then goes up. So our range is going to be y is greater than or equal to -4. So if you look closely at this particular function, you'll notice there's no absolute value or quadratic. It's just an x value surrounded by some numbers, which means this is our linear parent function, which has the equation f of x is equal to x. So if we start and we take a look at the parent function, we have our x, y table to help us, and if we look back at our notes for this, our x values go -2, -1, 0, 1, 2, and our y values do exactly the same thing. So if we graph this particular function, we have a diagonal line. So there's our parent function there in black. Now we take a look next and it says describe how this transformation will impact the parent graph. Well, I notice I have two things going on here. I have an a value equal to 5. Now because there's nothing inside of parentheses with x, I have no h value here, and this 7 on the outside represents my k value. So from here, we're going to take a look and we're going to look at these one at a time because one is a stretch shrink and one is a movement. And we always are going to start with this a value here. So always start with the a value if there is one. And this a value here is going to vertically stretch our graph by a factor of 5. So what it's going to do is it's going to take each y point in our table. So this is where we're applying our a value is equal to 5. And it's going to make each of these y values 5 times higher and 5 times taller. So we're going to leave the x values alone because it's a vertical stretch and the verticals deal with the y values, not the x values. So our x values stay the exact same. And our y values, our vertical values, get 5 times taller. So -2 times 5 is -10. -1 times 5 is -5. Then we have 0, 5, and 10. Now, if you'd like to draw this on your coordinate plane, you can, but we aren't quite done yet because in addition to this, we also need to account for this k is -7. Remember, k values represent a vertical shift. So this is going to move the graph that we currently have in red down 7 units. So there are two ways to go about this. You can go to the point x is -2, y is -10, which is down here, and then move it 7 points lower if you'd like. So you can actually go to those points and move them 7 points lower. The other option you have is you could create another table and say this is where I'm applying my k equals -7, and this is going to move you down, which is going to deal with the y value. You can take all these y values and you can move them down and you can subtract 7 from each of those y values. So you'll leave your x values alone because you don't have any sort of horizontal shifting going on. But you can take all of our y values, so -10 minus 7 is -17. -5 minus 7 is -12. 0 minus 7, -7. 5 minus 7, -2, and here we have 3. So again, if you'd like to go to each point and just move them 7 units down, that is perfectly fine. The other option is to just take all of your y values and shift them down by 10. So if we plot the points that fit on our graph, we have 0, -7, that fits right there, 1, -2, that fits right there, and 2, 3. So we can see that this graph is steeper because of that vertical stretch, and then it moved the entire graph down 7 units. Now the last thing we need to do here is identify our domain and our range. And what's really great about linear graphs is you can see that these linear graphs, because they're diagonal, go forever to the right and left, forever up and down, and as a result, both of their domains and ranges are all real numbers. So you can put that for both. So in this example, we're looking again at another quadratic. You can see this child graph has a squared. This is going to be a quadratic graph, which means that its parent function is f of x is equal to x squared. So we refer back to our notes here and we look at, well, the parent function is going to be x's are -2 to 2, and then it goes 4, 1, 0, 1, 4. So if we get that graphs now, so we have -2, 4, -1, 1, 0. So there we go. So there we have our U-shaped parent graph in the mix. So we can now compare our child graph to our parent graph. And now if we take a look at these transformations here, we have an A value equal to a -1 that I see, and we have an H value there in parentheses, so it's H is equal to -2. So remember, if we have an A value that we need to deal with, we deal with that first. So here we have an A value equal to -1, and what this A value of -1 is going to do is it is going to vertically flip our graph over. So in order to vertically flip our graph over, we're going to have to alter the y values a little bit, and we're going to vertically flip them over by multiplying all of these y values by -1. Basically going to take all of those values and take them from the upper two quadrants and flip them down below into the lower two quadrants. So our x values stay the same because there's no horizontal flip going on here. It's just a vertical flip, so we deal with the vertical y values. And we flip them over to get -4, -1, 0, -1, and 4. So to give you a little insight here, what we've basically done is we took all these points and we flipped them down. However, because we have two transformations going on here, we're not quite done yet. So the next thing we need to do is we need to focus on this H value here. And remember, H values deal with horizontal shifts. So they deal with the horizontal changes that are coming. So here we're going to move this horizontally, and we move it the opposite of what we expect. So since it's a negative number, we're going to move it to the right 2 units. Now notice, in order to move to the right, we're going to have to add 2 to all of our x values here. So in order to move those x values right, we're going to add 2 to each of them. Now again, just like before, you could plot the points in red and then shift them horizontally to the right. What I'm just going to do is I'm going to alter those x values, which are my horizontal values, and I'm going to move them 2 to the right by adding 2 to each one. So -2 plus 2 is 0, -1 plus 2 is 1, 0 plus 2 is 2, 1 plus 2 is 3, and 2 plus 2 is 4. So I took all those x values and I just bumped them by adding 2 to them, 2 to the right. And then my y values stay the same because this is a horizontal shift, not a vertical shift of any kind. So now if I plot these points, if I go to my graph, I can go to the point 0, -4, 1, -1, 2, 0, 3, -1, and 4, 4. So here what I see is this graph in purple is similar to the graph in black. What's happened is the graph in black got flipped over and then bumped 2 to the right. And you can see that taking place both in our table and in our graph here. So now our domain and range are our last two things that we need to identify. Because our graph is going forever to the right and forever to the left, our domain is simply all real numbers. And because my y values start at 0 and then go down, my range is the y values are less than or equal to 0. Now in this last example here, we're going to tie all of our knowledge of transformations together. So here we can see that our parent graph is going to be the absolute value parent graph because our equation down below has an absolute value in it. So I have f of x is equal to the absolute value of x. And we start with our parent graph here. So I'm going to graph that first. My parent graph for my absolute value function is -2, -1, 0, 1, 2. And then our y values are 2, 1, 0, 1, 2. So if I get those onto my coordinate plane, there we have it. There is our parent absolute value graph. Now, our next step here is we need to look at the transformations that are taking place. And here it looks like we have quite a few. So we have an a value that's equal to -3, an h value equal to -1, and a k value equal to 5. So we need to always start with this a value here, because if we have an a value, we need to stretch it or shrink it first. So here we have an a value equal to -3. This tells me that I'm going to flip it vertically because of that negative attached to the 3. And then the 3 itself tells me I'm going to vertically stretch by a factor of 3. So, in order to vertically stretch by a factor of 3 and vertically flip it, I'm going to take these vertical y values of my parent graph and I'm going to multiply all of them by that -3. And in doing so, I'm going to flip them and stretch that graph to be 3 times as tall. So 2 times -3 is -6, 1 times -3, -3, 0, then we still have -3 and -6. Now my x values are going to stay the same because this is a vertical stretch and a vertical flip, not anything to do with those horizontal values. Now, these next two we can actually do simultaneously together. So, h and k represent the different shifts of how we move this graph around. So h represents that horizontal shift. Remember, it moves the opposite of what we expect, so we're going to move right 1 unit, which becomes a +1. Our k value is going to move our graph up 5 units, so a +5. So we can take these values in our table and we can apply them accordingly. For h, we're going to add 1 to the x's, and for k, we're going to add 5 to the y's. Remember, h works opposite of what we expect. So here for the x values, we want to move them all 1 to the right, so we're going to add 1 to each. So those become -1, 0, 1, 2, and 3. For the y values, we're going to take those and we're going to add 5 to each of them because we're going to move them all up along the y-axis 5 units. So -6 becomes -1, -3 becomes 2, 0 becomes 5, -3 becomes 2, and -6 becomes -1. So now if we go over to our graph and we actually plot these points in purple, we have -1, 1, 0, 2, 1, 5, 2, 2, and 3, -1. So what we see here is kind of what we expected to see according to our transformation. So we have flipped the graph, it's stretched to be skinnier and taller, and then the graph, all of those points moved right 1 by adding 1 to the x values, and up 5 by moving 5 to the y values. Now our last thing here is to find the domain and the range. So our domain, because our graph is going forever to the right and to the left, is all real numbers. And our range, we start at 5 and it goes down. So we have a range of y is less than or equal to 5.